Factoring by graphing. We can factor using a graphing calculator, which is a nice, quick, easy way to do it. Yes, you should know other formal methods because graphing calculators are approximate, and we'll see that as we go through our examples. But if you're struggling, it's good to jump into the graphing calculator, get an idea, and move from there. So let's think about what happens with factoring by graphing. The thing you want to remember is standard form is this nice simple ax squared plus bx plus c. And there's two factored forms. The simple factored form is some constant a multiplied by parentheses x minus s and more parentheses x minus t. And what you should remember about this form is that s and t are the zeros, that is to say the x-intercepts on the graph. There's distributed factored form, which can be written some constant times x minus another constant, then some constant times x minus another constant. Remember this a, b, and c are not the same as this a, b, and c. All these letters that are not x represent is we're looking at some constant. So we want to get from standard form to factored form, and there's a lot of reasons in applied math you would want to do that. But let's think about some examples and look how graphing can help us. We're going to start with an easy example and gradually work towards more complicated. So in our first example, we have x squared minus 2x minus 15. Let's look at that example. Okay, so we're looking at x squared minus 2x minus 15, and the thing you want to remember is the factored form gives you the location of the zeros, that is to say the x-intercepts. So with a good graphing calculator, you can quickly find the location of the zeros. This one is at -3 and this one's at +5. Let's start by making the common student mistake as we enter this information. We're going to say x minus 3 and x plus 5, and we made the classic student mistake, so our graphs do not match. So the first thing we're noticing is that the graphing calculator not only helps you quickly determine your answer, it helps you determine whether you made a mistake. So what happened is our parentheses should have minus, we put plus. Let's switch this to plus and switch this to minus. So now we're looking at x minus the 0, the first x-intercept, and x minus the second x-intercept. What we have to remember is minus a negative is the same as plus. So very quickly, without having to think about all the various steps, we got the factors of x squared minus 2x minus 15, and we corrected a common mistake, and we all did it in a matter of seconds, simply by trusting our graphing calculator to guide us through the process. Let's now take on another example, 3x squared plus 5x minus 8. How can we factor this one? This one is a little trickier, so we want to think about this in two steps. So we're going to go to our graphing calculator again and think about the various steps. Now, on our graphing calculator, we can see that we're looking at 3x squared plus 5x minus 8, and we can see we have a factor there and a factor there. Let's work with this idea. The first thing we notice as we're looking at that minus 2.667, if you're really good with your fractions, you might recognize that that minus 2.667 is, well, repeating is 2/3, and another 2 gives you 6 more thirds for a matter of 8/3. So we can see it passing through the right points. Now let's go a little bit further and say our other point was +1, so we're going to say x, remember the minus on the inside, -1. Now, we have our factors correct in a way, but there's something missing. How do we know something's missing? The curves don't match. Notice that 3 in the front of the first one. Let's just take it and put it in the front of the second one. Now our curves match perfectly. So that 3 in the front stays in the front, and we have now successfully factored our equation, our standard form is now in factored form, simple factored form. There's one little challenge, though. Most standardized tests and most textbooks are going to want this changed into um, distributed factored form. So now let's think about that for a minute. Now, from a graphing calculator, we quickly got this idea that our 3x squared plus 5x minus 8 factors into 3 times parentheses x plus 8 thirds times parentheses x minus 1. And we said that's not going to be the form most standardized tests want this in. But notice only one of our parentheses has a fraction. So let's take that 3 and distribute it through the parentheses that has the fraction. That's going to give us, as we distribute, 3 times x, and 3 times 8 thirds, those 3's cancel, leaving just 8. And of course, we keep the other parentheses. We don't distribute through there, we just keep that. So simply by distributing the 3 through the parentheses with a fraction, we now have it in the form that is going to appear on a standardized test. Let's check that. So after we distributed, we said 3x plus 8. And then we said we're going to keep that x minus 1. Notice how it's a perfect match. It's got just the same zeros, which are your solutions there. It's an exact match to the curve. So the answer you're going to see on a standardized test is the second one. The first one is technically correct, and it is useful in technological applications, but the second one is the one you want to see in your math class. Let's take it to another example, slightly more challenging, but still pretty straightforward. We have 6x squared minus x minus 2, and we're going to say, can we factor that one by graphing? Are there any tricks we have to pay attention to? So let's look at what we're going to see on the graph. We see our 6x squared minus x minus 2. Well, there's our minus 0.5, and there's our 0.667. That is 2 thirds. So let's do our factoring process. First, we're going to say the x plus the 0.5. And then, well, we could have written that as a fraction, but let's hold that off for a minute. X minus the 2 thirds. Now we see that our points match again, just like they did before. What is missing? Well, that 6 multiplied in the front. Let's bring it down like we did before. Now we have a perfect match. The curves are laying on top of each other. So in terms of our simple factoring, the one that is good enough for most technological applications, it is successfully factored. Oh, let's remember before we move on that 0.5 is 1/2. Yes, it's still correctly factored. Now let's think about that. How do we get this into the type of factoring that you're going to see on a standardized test in a math class? We got it in the simple form. We want to get it into distributed form. So let's go back and think about how we can do that similar to the previous problem. All right, here we have it, our 6 minus, or plus 1/2 and our minus 2 thirds. What can we do? Now, we'll notice there's a fraction in both parentheses, and let's think about that for a minute. The one has a denominator of 2, and the other one has a denominator 3. Well, think about that for a minute. 6 is 2 times 3. Let's put that down here. And take the 2 and distribute it through this one, and take the 3 and distribute it through this one. So we see a 2 and a 3, and we know 6 is 2 times 3, so let's distribute that way. We get 2x, the 2 in the numerator and denominator cancel, leaving just 1, and we get 3x, and 3 times the denominator 3 cancels, leaving the numerator 2. So now we have turned it into your distributed factored form. Let's go back to the graphing calculator and test and see if that really works. Okay, we're back at the graphing calculator to test whether the distributive method that we just tried worked. And we got 2x plus 1 when we distributed the 2 through. And we got 3x minus 2. Notice they're a perfect overlay, so we did distribute correctly. We were able, using this graphing trick, to go from standard form to simple factored form, and then just paying attention to our denominators, go from simple factored form to distributed factored form. We've succeeded on this one. Let's finally look at this last example, 6x squared minus 3x minus 2. This one looks like it'll work just like the one before, and you can imagine that you're going to break up the 6 into 2 and 3 and distribute them through. But let's look at it and see what actually happens. So here we are, 6x squared minus 3x minus 2. And our first zero is this 3.79, and our second zero is this 8.79. A little bit of reasoning here might tell you that that's probably a longer decimal that got rounded by the graphing calculator, and that's a longer decimal that got rounded by the graphing calculator. Now, when I think about 6, it has factors of 2 and 3, which could give us denominators related to 1/2 and 1/3. Neither of these decimals look like they have anything related to 1/2 or 1/3. What that tells you is that this can't be factored completely using your traditional method. You're going to have to use another method. So this one does not factor nicely, and you can tell that simply by recognizing that these decimals don't make sense with this starting number. Let's actually take this problem one step further into another. So we've looked at some that factor simply, some that require you to move to the distributed factoring method for a math class, and some that will not factor in the normal way. If you've already learned the quadratic formula, you're going to use that for this problem. But let's go one more step here and look at this problem. You notice very quickly that this parabola does not cross the x-intercept, the x-axis. It has no x-intercepts. So you know this problem does not factor, that is to say it does not factor without using complex numbers. So very quickly we were able to identify whether something factored simply, whether something factored into distributed form, whether something did not factor easily at all. That was this last problem, or whether something cannot be factored. This one did not factor easily, and the other one, the last one we showed, does not factor at all. So factor by graphing. If you're in a panic situation and you don't know what to do, factor with your graphing calculator first, or use the graphing calculator to check your work, and then you can tell whether you got it right by the other method that you used.